Okay, there you go. Again, in the last session, we discussed the stress strain behavior of a mild steel. Okay, so we did that. We very easily could have looked at the yield strength and the ultimate strength by looking at the stress strain curve. Like if you remember, I'm talking about this stress strain curve. Like it's very simple. Like you can very easily pick the FY, and you can very visually it is possible for you to look for the ultimate strength of this material. But when we when we are using a high strength, high alloy steel, so if we look at the stress strain curve of that high alloy steel, so you will see a different type of curve. This curve, it does not have that predefined plastic region. Okay, it does not have that defined or very visible Fy or the yield strength. So when we have this type of behavior, which is of high strength steel, so we cannot locate the yield strength. So what we do that we use a method we call 0.2% offset method. So this method is used to determine the yield strength of high strength steel. So how do we do that? So 0.2% means 0.002 strain. So what we do that, okay, I will go to the pad, my writing pad. So let me pick the pen. Okay, what we do that, where is my pointer? Yes, there it is. So you have to draw a tangent. Okay, tangent. Tangent. Okay, you have to draw a tangent. Why? I'm sorry. Yes, you have to draw a tangent. Okay, like this. There is a tangent. I'm sorry for my irregular line. Then you go to the string and you pick a value which is 0.002%. Okay, you draw a parallel line to this tangent. Okay, parallel line, you have to draw this parallel line. Okay, and the point at which this intercepts the original stress strain curve, we call it yield point. Okay, so the 0.2% or the 0.2% offset method is used to locate Fy, yield strength for high alloy steel. So so because the Fy is not visible, so over here we know that this is the peak point. Okay, so this is the Fu. Okay, and this is the Fy. So for high strength steel, we use the 0.2% offset method to locate the yield stress or yield strength. Okay, is that clear to all of you? समझ आ गई आप लोगों को?
Yes, sir.
Okay. Now let's have a comparison between different types of steel. So in this slide, you will see that there is a stress strain curve of a A36 steel. So you have a high strength, low alloy carbon steel. The stress strain curve for this steel is also shown on this slide. And there is another steel which is A54, quenched and tempered alloy steel. Okay, so the stress strain curve of that steel is also shown. So you will see that if you use the A36 steel, it will have a very low yield point, and it will have this ultimate point Fu, which will be somewhere 58. And if you use A572 designated steel, which is a low alloy carbon steel, so it will have slightly more Fu value compared to the A36 steel. Okay, the yield strength of A572 steel will be more than A36 steel. Similarly, you will see that A514 steel, it will have a more higher yield point, which is about 100 ksi, and this 57572 steel has a yield point of 50 ksi, and A36 steel has 36 ksi. Obviously, the yield point and the FU value, ultimate strength value for 514 steel will be higher. But the difference between these, if you use 514 steel, so you will have this highest yield. You will have a higher ultimate strength. But the ductility in this material will be very less. Very less. Ductility will be less in this material as compared to this material and this material. And the increase in the high alloy steel is due to the different components of the components which are used in the steel alloy other than carbon and iron, but they increase the strength of this material, but at the same time they reduces the ductility or the elongation in the material, so you will not have a ductile failure if you use this material. Obviously you will have a higher strength, but you will have reduced ductility, and this strength, increase in the strength, is also due to the heat treatment of the steel. There are different processes which are called quenching, annealing, hardening, that are carried out, or they are passed through those processes. And if you pass them to the heat treat, we call them collective pass steel through heat treatment, so the strength of the steel will increase. Okay, by strength we means yield and tensile strength, ultimate strength. Okay, so in the A572 steel and A36 steel, the heat treatment has not been carried out, and they have lower yield and ultimate strength, but their yield point are well defined, and the ductility in this material is more. For example, you want to use this material, so you will have a ductile failure. If you use this material, this will also have a ductile failure. But if you use this material, so it will, the failure may be brittle, there will be brittle failure, there will be not ductile failure. So it is important to see the behavior of these steels before shapes for these materials. So you have to decide which material you should be using for your structures. This one, or this one. Obviously you will go for this one, okay, or this one. Okay, now we come to the structural shapes. As I told you that in the reinforced concrete design, you have been using regular structures like rectangles, like squares, T's. But in the design of steel structures, you have to select some cross sections. Cross-sectional area will be selected from some well-defined shapes. So these shapes are, we call them, they are known as wide flange sections or X sections. If you look at this section, it is like H. Now they are designated by specific nomenclature. The first stem represents the shape W section or wide flange section. So this part of this wide flange section, we call it web. This part we call it flange. So it's a wide flange section, X section. The first term in its designation represents the depth of the section. The depth of the section in inches, okay? The second term represents the weight in pounds per feet. Like in the third dimension, like what is the weight of this section per length? It will have, the cost will be more, okay? You have American Standard section, which we designate with S. So look at its nomenclature, like it is S1870. So this section has 18 inches depth, and the weight of this section in pounds per feet in this direction, the third direction, along the length, it will have 70 pounds per feet. This section, the two sections have the same depth, but this section is heavier than this section. Now you have to choose cross-sectionals, use compression, tensile section members from this section, and most of the time we use this section. For columns, for beams, you use this section. Now there are other definite shapes, we call them angles. Okay, there are two types of angles you will see. One we call equal leg angle, the other we call unequal leg angle. In equal leg, like these are the legs, they are designated with alphabet L, and it is 6 cross 6. 6 means 6 inches length of first leg, length of second leg, and 3/4 means the thickness of this angle. There are some unequal angles like the 6, 4, 5/8. 6 represents the depth, this leg, then this length by the thickness. Similarly, we have channels or American Standard channels. So if you look at this shape, so it is C. They are designated with C. C9. 9 represents the depth of the section, and 20 represents the weight in pounds per foot in this direction. Okay, along the length. Okay, so these are some of. Then we have the structural T. So this is designated with VT. VT means that T cut from wide flange section. If it is cut from a wide flange section, we call it WT. And you know that 18/115 means that 18 is the total depth of the section, and 115 is the weight in pound per feet along the length of the member. So these are some of the cross sections you have. You will see that in the demonstration examples we will be using them. We obviously there are bars which you can also use. Like there are generally there is a you can use bars. Bars are those members, steel members or shapes which have width less than 8 inches. If the length or the width of a rectangular section is more than 8 inches, we call them plates. Okay, then we have steel pipes, we have hollow structural sections, so they will be designated as, most of the time we will be using a term we call HSS, hollow structural steel. Okay, then you can use a wide flange section together with the current cover plates. Okay, for example, you need a section, the demand on your structure is very high, so you need a deeper section, and there are no predefined or standard sections which are that deep. For example, you have up to 20 or 18, but the cross section you need is about 40 inches. What you do? You combine plates and you weld them together. Okay, this is called a built-up sections. Okay, mostly we use these sections for the plate girders, the beams on which the demand is very high. Okay, we use these sections for those members. Then we can use a combination of angle, we call them double angle. We can use, if the cross-sectional area, required cross-sectional area is more, so we can use the double channel. Okay, so these are some of the shapes or combination of the shapes which you will be using for the design of steel structural members. So any question from your side? Any comment?
No, sir.
Is that clear to all of you? आप सबको क्लियर हो गया है कि वो कौन कौन से shapes हैं, what are the names and what are the geometrical shapes?
Yes, sir.
Okay. You are clear about plate girders, like once you don't have deeper sections,
Yes, sir.
what you do? you weld them, you join them together to come up with a shape. Okay. Okay, as I told you that there are two type of sections, cross-sectional sections, hot roll sections and cold roll sections. Okay, what are hot roll sections? Okay, let me go through its the text. Hot roll sections are those sections in which are molds when the steel is still hot. It is not allowed to cool completely. For example, you have some steel and you are producing that steel in a furnace. Okay, the steel is in the molted form. So what you do, you have some shapes, geometrical shapes like this shapes. What you do, you pour the like you pour the molted steel like this, molted steel. Okay, molted steel or molten steel, whatever you want to call it, molten steel in shapes, predefined shapes, and you don't allow it to cool completely. Okay, when you pour in this shape, or what you call casting, you do the casting, the steel is still hot and it is turned into this shape. So the section produced while steel is not allowed to cool completely, when you pour the steel in the molds, so this such type of sections are called hot roll sections. Okay, so the hot steel passes through a series of rollers that squeeze the material into desired cross-section shapes. Rolling the steel while it is still hot allows it to be deformed with no loss of ductility. If you have steel and it is not cooled completely, and you molded it into some shape, so it will have the same properties as the molted steel, so there will be no loss of ductility, so there is no cold working of these sections. Okay, what are the shapes of hot roll sections? We have already discussed. We have wide flame, we have American beam, we have channels, we have angles, we have wide flame T, we have beam T, we have pipe, we have structural tubbing. Also, the nomenclature of these sections is also mentioned on this slide. Okay, so this is hot roll sections. So we will be using hot roll sections for design of our structural steel members. Okay, what are the cold steel members? For example, so cold steel members are those members which are created by bending already casted shape or bending thin plates at room temperature. Like the steel you have produced, you have a shape, you have produced this plate, for example, and you have, it was originally a hot roll section. Oh God, why it's not ready? Hot roll. It was hot roll. Okay, and it is cooled, and you have brought it from factory. It is placed, say, in the structural engineering or structural testing laboratory, and you want to change its shape. And what you do the bending. So this type of shapes produced by bending or molding the shape of the members at room temperature. We call such members as cold form members or cold form sections. So they are not used as a main carrying load members like purlins and girths. Okay. So we are not concerned with cold sections. We will be not using cold form sections. But for the sake of completeness, like I wanted to add, I added that in the slides that you there. So for hot roll section, we use AISC. And for cold roll design, there is another code, AI Do you know what is the abbreviation of that code? Anybody from class? This is for hot roll. You know that? Do you remember? What are the specifications
Association
for?
of steel construction.
We have to go to the first slide. I also cannot remember its name. I'm sorry. This one. AISI. This cold form steel sections. Yes, AISI. Yes, this one. This is for cold form members. Okay. So in this slide, you will see the different shapes, cross-sectional shapes, and what are their preferred steels. Okay. Mostly they say angles. Where if you want to use angles, the preferred steel is A36 steel. Okay. If you want to use plates, you want to use beams, you want to use wide flange sections, so it should be conforming to this material. Okay. But we will mostly use this steel. Okay. Okay. This is just a recommendation. If you want to use this section, it should be made of this material. Okay. This material like beams and what else, channels. It can be either A36 or they can be either 572. Okay. Now this is the repetition, like this is a wide flange section. What is the symbology that is representing? Like we have already discussed, the W represents the shape, 18 represents the depth, and 50 represents the weight in pounds per feet. Okay. Similarly, how angles are designated. Okay. So what are the different tension member design? What should be the cross-sectional shapes you should be using while designing or a tension member? These are the shapes which you will be using when you are designing a compression member. You can use wide flange, you can use double angle, structural T. So combination of these sections, built-up section, you can also use built-up sections. Okay. So so this is about beams. If you want to doing a design of beams, you should use wide flange sections. Okay. Or American beams. Okay. Okay. You can use open web joist. Okay. Now these are some of the steel structures like the Eiffel Tower, the James Thompson Center. They have been constructed using steel. Okay. Iron. So you can see the geodesic dome at Walt Disney. It's a very attractive structure like this one. We have the Golden Gate Bridge, like it is also constructed out of steel. Okay. You have Taipei 101 Taipan, this building. You have this Beijing National Stadium in China, which is constructed out of this steel. So as I told you that we have three different CLOs. The first CLO we have targeted to give you theories and models which will enable you to design and analyze a steel structure members. So the second was to analyze, we have to build capacity in the students so that they can analyze a tension, compression member under axial loads, beam under flexure and shear, and also connection under axial load. So I have added some of the problems from your book. Okay. And they are very simple problem. If you go to Segway book and you go to their problems, you will find this problem 1.54. So this problem is about a tensile test that was conducted on a specimen with a diameter of 0.5 inch. A strain gauge was also attached to that specimen, which were recording the strain when that bar was loaded. Okay. So the strain measurement, you need this strain gauge. Okay. The following data was obtained, like the load versus the strain. Okay. Now what it is asking you to create stress strain values. So you have the load. Okay. and if you divide that load by the area, so you will get the stress. And do we have we already have strain. Okay, so you can convert this load table into strain like this. Okay, what else it is asking you? It is asking you to plot these data points and draw the best fit straight line through them. So what you do, you plot this data, the stress versus strain. On y-axis you have the stress, on x-axis you have the strain. If you plot this data, this data is represented by these blue rectangles or squares. So then you have to draw a line which is representing this data. So in Excel it is very easy, you can do it. You just draw this figure first. It will have no line, but when you right click on Excel, so it will give you an option, add trend line. Okay, but so in Microsoft Excel, like in Microsoft, yes, in Microsoft Excel, so if you have a graph, a plot of data like this, and this, and this, and you don't have a line, so what you do, you right click on the data. Okay, you will do a right click with the mouse, and you will add, it will give you an option, you will add this, add trend line. Okay, so it is like doing regression analysis. So it will automatically plot a line which will be representing the mean behavior of this data set. So in this way you can obtain this line. Okay, so what you do, it is a straight line. It means it is representing the, in the stress strain behavior of the material, it is representing the elastic region. So if you take the ratio between the stress and strain, okay, so it will give you the modulus of elasticity, or the slope of this line will give you the modulus of elasticity. Okay, so this was asked in this problem, that what is the slope of the line? It was actually, it is asking you to compute the modulus of elasticity. Okay, so this is a very simple problem. I hope you can do it. Then there is another problem. The data shown were obtained from a tensile. Again, these are the results of a tensile test specimen with a diameter of 0.5 inches and gauge of 2 inches. Okay, 2 inches is the gauge length. Okay, whenever we do the bar testing, oh my, why it is not? We do bar testing. Bar. This is a bar. So we use a gauge length. Mostly in the structural material testing lab, we use 8-inch gauge length. Okay, so in this example, the gauge length is 2 inches. The specimen was not loaded to failure. Okay, now you have to generate table for stress and strain. The load is given, elongation is given. The cross-sectional area is 0.5 inches. So you can very easily calculate stress by this load divided by the cross-sectional area. So you can calculate the stress at this point, this point, this point. You already have the elongation. From this you can calculate the strain. Let's see. So the load is there, elongation is there. So stress is calculated and the strain is calculated. Okay, now you know how, or what is the formulation, how elongation, what is the formulation for calculating the elongation. So you can go back to the slides. So from there, if you know the initial length, so you can calculate this final length, and accordingly you can calculate the strain. Okay, so you can calculate the strain. Okay, Once you have calculated the strain, you will plot the data. Okay. Now you can see this is a stress strain curve, and it does not have a defined Fy value. So what you are going to do, you are going to use this 0.2% offset method. Okay. So you are going to select a strain and you are going to draw a tangent. Let me draw a tangent. Can I do that? Yeah. Draw a tangent. And you have to project this line parallel to this tangent. And where it meets this curve, this will be your Fy. Okay. Fy. It requires you to calculate this Fy. It requires you to calculate this proportional limit. So this is the proportional limits, like the tangent, and they are coinciding with this portion of stress strain curve. So this value will be your proportional stress. Okay. So obviously I want you to go through these examples. Okay. And there are other problems which are given at the end of chapter number 1 of the Sequoia book. Okay. So if you have any difficulty, so you can come back to me so I can help you out with it. Okay. So these are very preliminary examples, so to get you started. Okay. So now there is a practice problem. So you have to find the strain in the member AB. There is a member AB. This is a truss which is axially loaded, and the strain in the member AB is about 8.9 into 10 raised to power minus 4. The strain for this member is given, and the member is L3, 2.5, and 1/4. It means the length, this is an unequal angle. Okay. The length of the legs of these angles are different. The thickness of this angle is 1.4 inches, and you are using a A3060. Determine the following. We have to find the change in length. Okay. What is the force in the member? But we know the vertical size. Okay, this length of this member is given. Okay. Now you can use the trigonometry to calculate the length of this member. Once you calculate the original length, so using this strain formulation, which is, let me go back to my pad. Okay. Writing pad. Yes. We know that strain is equal to length, a change in length divided by the original length. So you have to compute this length using the trigonometry principles like sine or cos of something. You have to come up with the length. So that you can, once you know the strain, you already know the length, strain, you know the length. Once you compute that length, you can calculate the change in length. Then you can calculate the force in the member. Okay. So you can use the method of giants or method of sections to compute that. Okay. I have the solution to this problem. So if you have any problem, so regarding solving this problem, so you can ask me, I can give you the solution. Okay. So with this, I would end today's lecture. It was a bit lengthier, but now whatever time is left, so you can practice these problems. Okay. So thank you very much. Any questions?
Yes, sir. सर ये proportional limit और ये elastic limit में फर्क करवा दें.
You are very not that audible, but what I have understood from your question that what is the difference between the proportional limit and elastic limit? So the difference,
Yes,
there is no difference because the Hooke's law is valid for the both limits, and the stress is proportional to the strain. Okay, but just for the demonstration purposes, that we are entering, or the material will enter into inelastic region from elastic behavior, like the material will go from the elastic behavior into inelastic behavior. So that's why this point has been divided into 2 points, like one is the proportional limit, the other is the elastic limit. Or you can say that the elastic limit like is representing the transition from elastic limit, the material is entering into the non-linear range or the plastic range. That's why in order to demonstrate this phenomena or this feature, so the elastic limit has been divided into proportional limit and elastic limit. There is no other difference. Hooke's law is valid, but you can see that we always used a. Is that okay? Hello?
Okay, sir. Got it.
Sorry?
Thank you, sir. Got it, sir.
Okay, thank you very much.
Sir,
Thank
got
you
it.
very much. I understood. Thank you. So I would ask you to go through this problem. We have time up to 10:45. Do you have copy of the slides?
Yes, we have.
Yes,
Okay.
sir.
So why don't you try this problem? So once you do this problem, you will understand, okay, what is the Fy of this material? You will say Fy is 36 KSI for this material. Okay. So we have
Okay, sir.
time. Okay, try it out. So I will stop the recording and I will be in the class up to 10:45, okay?